Hey everybody, welcome to today's video, which is an introduction to photoelectron spectroscopy. That's a mouthful, PES for short. So you remember we've talked about ionization energy, which is the energy needed to remove an electron from an atom. Of course, energy is needed because Coulombic attraction between the positive protons and the negative electrons is holding them in place. Okay. We learned in an earlier video that the photoelectric effect showed us that photons that had enough energy could dislodge an electron from an atom. That's what's going to happen inside this device. So let's suppose that we have lithium in the device and our high energy photons have an energy value of 100. I'm using just real simple made up numbers for this explanation. So along comes this photon. Remember, it's not a physical particle. It is simply a quantum or a packet of energy. And if that photon happens to strike this electron, it will dislodge it. And the dislodged electron leaves the atom and just travels along until it hits the detector. And as it hits the detector, it registers a value of 40. Okay, now here's what the PES machine interprets that as. 100 is the value of the photon, that's known, and it strikes the electron. It uses some of that energy to remove the electron, and whatever's left over is recorded when the electron strikes. Do you see how that difference is 60? So that is the energy that was needed to remove that valence electron. That's the ionization energy for that valence electron. Okay, here comes another photon, also has an energy value of 100. And as it zips along through the device, it happens randomly to hit, for this lithium atom, one of its inner electrons. This is totally random. These guys are so high powered, they can hit an easy to remove valence electron or a harder to remove inner electron. So here comes the photon, the little bundle of energy. It strikes this electron. By the way, once an electron is dislodged from the atom, it goes by the name of photoelectron. Okay, guys, those electrons haven't changed in any way. They're just simply knocked loose from their atom by a photon. Okay, so this guy was hit with a photon whose energy was 100, and when it hits the detector records 20. Okay, the photon packed a punch of 100, and when the electron hits the detector, there's only 20 left over. So the difference between those gives you a binding energy for this inner electron, a binding energy of 80, or ionization energy for that inner electron, energy needed to remove it, was larger, 80. Okay, I'm going to send one more photon through the machine. Can you see that the likelihood of that photon striking another inner electron is twice as much as the probability that it would hit a valence? And guys, that's just the randomness of these high-powered photons, and it's because in our collection of lithium, there are twice as many core electrons as there are valence electrons. So here comes my next photon. energy value of 100. It randomly hits this electron, knocks it loose. The detector records 20. So we say the photon hit with 100. When the electron hit the detector, there was 20 left over. So it must have taken, again, 80 to remove that inner electron. Okay, now this is what the spectrum generated by the machine will look like. This is a PES spectrum for this element, lithium. It shows us two peaks. The peak that represents 80 for the binding energy, these two guys, is twice as tall as the peak for those that were held with binding energy of 60, the valence electrons. And the reason this peak is twice as tall as this one is because there were twice as many of them as the easier valence electrons. Okay, let me show you a spectrum for another element, and I'm not going to tell you who it's for. This is one of the tasks that you all need to be able to do, is to interpret a PES spectrum and identify the element that it represents. All right, so here's binding energy, or it could also be labeled ionization energy. They're essentially the same thing. Notice that that axis is always numbered kind of backwards, with the bigger values at the left working its way down to the smaller values. And then the y-axis is photoelectron intensity. How many dislodged electrons are observed? So for this electron, we have a peak here with the highest binding energy. So that must represent our electrons that are closest to the nucleus. In other words, 1s. And you see how tall this peak is? That's 1s2. And then we have another peak, and these electrons are apparently held with much less binding energy, so they're not as close to the nucleus. This would represent 2s. Notice the intensity of the peak is the same size. So 2s2. And then we have another peak showing electrons held with even less binding energy. In other words, the energy needed to remove them is smaller. This would be 2p, and it is 1, 2, 3, 4, 5, 6 for the intensity. Then we have some other electrons held with even weaker binding energy. This would be 3s2. And lastly, our weakest held electrons for this element would be in 3p. And the intensity of that peak is not 2, but 1, 2, 3. This is 3p3. So once we've labeled our peaks, we can use our periodic table to determine that element ended in 3s2, 3p, 1, 2, 3. This must be the PES spectrum for the element phosphorus. So I'll give you guys some practice looking at PES spectra, and you'll identify which element it represents. And then in class, we'll do some more detailed work interpreting these spectra. Okay, guys, hope that was helpful.